everyone. Thanks for joining us for the CIIR Talk Series. I'm Zamani, and I will be moderating this talk. Today, it's our pleasure to host Biega, who is a Tenure-Track faculty at the Max-Planck Institute for Security and Privacy in Germany, and she works on designing legally, ethically, and socially responsible information access and social computing systems. Before joining Max-Planck Institute, she was a postdoc at Microsoft Research Montreal. Actually, I think we had some joint. We've been at Microsoft jointly at a time. And she's been working in the faith group in Microsoft Research Montreal. She completed her PhD in another Max-Planck Institute for informatics and one for software systems. And her PhD work led to the 2021 DBIS dissertation award of the German Mathematics Society. And she also had a lot of industry experiences working with privacy infrastructure at Google and doing some consultation for Microsoft product teams. And today, Asha will talk about operationalizing legal and societal constraints in information access systems. Asha, please.
Great, thank you, Hamed. Thank you for the invitation. I'm thrilled to be here, thrilled to connect with all the UMass people. Could I confirm that you can still see my slides? Okay, that's great.
Yes.
Yeah, what I want to talk about today is work that we do that interfaces computer science, or more closely information retrieval and information access systems, and tech law. And talk about some of the work that we do operationalizing concepts from data protection laws to make them implementable in the context of practical information access systems, but also work that we do in collaboration with legal scholars to provide some insights from practical deployments and research observations we make to actually help them refine these laws. So I want to just very briefly begin by telling you what I mean, or how I see an information access system for the purpose of this presentation. So we see these systems as two-sided systems. We have two different groups of people. We have users, that is consumers of information, who interact with the system via an interface. We have a service provider who runs an underlying algorithm and that takes as an input a corpus of documents and, for example, ranks them to present them back to the user who is the consumer. And thinking about applications related to personal data, we think of the corpus as belonging to people, or as representing people. So the items that we, for example, rank in search systems and recommender systems can be either people themselves, or their profiles, or these can be items that are created by people. For example, in sharing economy platforms or platforms such as music streaming platforms, the items that we rank are actually created by people. So this is a second group of users whom we consider in these systems, and these users we often call producers. In a specific instantiation of this very abstract depiction of what an information access system is a search system. So we have a searcher who issues a query to the service provider. The service provider ranks an underlying ranking mechanism that then ranks the documents from the corpus. Again, these can be either search subjects or items that were created by these search subjects. And the interaction between these two different groups of people is that search subjects, or the items that they produce, are exposed to searchers, and searchers, as a result, pay attention to the search subjects. So in a sense, attention is a form of currency in this platform. And the questions that we're asking ourselves in the context of this information ecosystem is what can go wrong? And specifically, we ask ourselves this question because the data that we are dealing with in the systems is often personal data. And so what happens is that different data protection laws kick in when we process personal data. So I mostly focus on GDPR, but a lot of the principles that GDPR specifies for respectful processing of user data are common to other data protection laws as well. So examples of these processing principles include lawfulness, fairness, and transparency, purpose limitation, data minimization, accuracy, storage limitation, integrity, and confidentiality. So now we have these two different worlds, right? So we have our information systems, and we have the data protection laws that specify how we should process user personal information, personal data within these systems. And the law is very often very vague as to how these principles are specified. And this is for a good reason, because we need some room to interpret these principles in specific contexts. But this is not what we as computer scientists need to implement these principles in practice. We need specific mathematical definitions. We need to know very precisely how to translate these principles into code. So what the work in the space focuses on is, on the one hand, providing these specific definitions, so giving instructions as to how these principles should be implemented. And on the other hand, when we dive deeper into trying to implement these principles, we get some insights into what is easy, what is difficult, what is not doable, just because of the computational limitations that we can then offer back to the legal community so that they can refine these laws appropriately. So in this talk, I want to present some of the work that we've done implementing, operationalizing some of these principles. And I want to start with the principle of data minimization. So Article 5 of GDPR defines data minimization as follows. Personal data shall be adequate, relevant, and limited to what is necessary in relation to purposes for which they are processed. And so there are two components or two questions that immediately sort of jump out from this definition. So first, what does it mean? What is the purpose of personal data processing in the context of systems that we're thinking about? So for example, personalized recommendation systems or search systems. And second, once we define the purpose, then how do we limit data in relation to this purpose? There has been a lot of discussion about this principle, and maybe in a sense it's considered a bit controversial. So on the one hand, we want this principle to be applied to data-driven systems because of various benefits we're expecting. So for example, we're avoiding unnecessary risks of personal data processing. For example, an infrastructure of a service provider can be hacked. We're preventing inference of personal information that is perhaps not explicitly there in the user data. We're giving users increased user control over the data. We're giving them some agency and understanding really as to what the service provider knows about them and how, how they can manage the data that they're producing. And we're also potentially limiting the opportunity for surveillance and targeting. At the same time, people recognize that there are lots of pitfalls related to data minimization. If we want to limit the amount of data that service providers collect about us, this can lead to curbing innovation. Arguably, the availability of all of the data that search engines and recommender systems have access to have led to a boom in these technologies. We might be limiting the opportunities for developing societally desirable tech. So for instance, search engines like Google can develop disease prediction tools based on the queries that people issue to the search engine. If we minimize the data, perhaps we won't be able to do these sorts of applications anymore. Third, maybe we're going to limit the competitiveness of companies that actually operate in the markets that need to do data minimization according to the legal regime. And finally, the final argument against data minimization that we've seen in the literature is that people say it's just impossible, right? We're living in a world of big data. Algorithms that we're creating need the data, which we just can't we cannot minimize data. It's just not doable anymore. And so in these discussions with legal scholars, especially this last argument that it's just impossible, is an argument that I have second thoughts about. And the reason for this is that there's a lot of empirical evidence in computer science literature that the data that we're collecting might not be actually necessary to reach a certain quality of a system. So for instance, in this paper from 2008, Krause and Horvitz looked at how the utility of a search system, as measured by the quality of the results in personalized search, changes as we collect more and more features about users. And so they observed that data collection exhibits a diminishing returns property. So as we collect more, we're actually flattening in terms of the performance increase. And we've seen similar examples in the context of other systems as well. So for instance, we observed this diminishing returns property in the context of deep learning systems, natural language processing, vision. So there exists empirical evidence suggesting that data collection helps us at the beginning to improve the model quality, but at a certain point, perhaps we should stop collecting the data when we think about the quantity. Data minimization is not only about quantity, though, it's also about quality. It's about the representativeness of the data that we collect, but also about whether the data we collect is sensitive. And so one of our older papers from CIIR 2017 looked at personalized search performance on a more fine-grained per user level. So there, our goal was not to limit the amount of data, but to see to what extent we can distort user profiles while keeping personalization quality. So essentially what we did is we merged all of the user data into a single pool and then reshuffled the data among the users, creating synthetic profiles. And without going into much detail, what we showed is that as we create user profiles that are less and less similar to the original ones, we do lose some quality, but perhaps the loss in quality is not that big, depending on the application, but it's definitely not drastic. And empirical evidence is of course, one argument, but there, in fact, exist computational techniques that can be thought of as minimization techniques. So techniques like feature selection or outlier detection or active learning, all in practice minimize the data that we collect. So we have empirical evidence. We have techniques that could be used to minimize data. Why isn't data minimization applied and implemented more widely in data-driven systems? When we looked at relevant literature and guidelines issued either for practitioners or by data protection authorities, what we've noticed is that, first of all, there is a scarcity of specific guidelines. And studies, user studies done with software developers showed that software developers generally don't understand what data minimization actually means and how to implement it. So everyone has their own interpretation. And we observed more specifically that there is a lack of operational definitions for personalization profiling in decision-making systems. So essentially, information access systems such as recommendation or search applied in personalized contexts. We looked at some guidelines issued by different data protection authorities, for example, in the UK and in Norway. And we've noticed that what they often do is they either don't talk about data-driven systems at all, but talk about more scenarios where you have very specific attributes like location or gender or age, and say, well, you shouldn't use this attribute in this scenario and this attribute in this other scenario. But they don't really talk about these data-driven setups where we collect behavioral data, such as clicks or search queries or product ratings. And very often they do mention techniques. So for example, they would say, look at how the learning curve looks like. But they don't give detailed guidelines as to what to actually do with this learning curve. And so having observed the lack of these specific guidelines, our goal in the line of work that we pursue here is providing specific definitions of what data minimization means in the context of personalized information access systems. I've mentioned this before, but the two components of this definition that we're focusing on is what is the purpose of data collection and how to limit data in relation to that purpose. And so having these two definitions, the third question that is important to understand is, if we implement data minimization according to these principles, what consequences will this have for the online ecosystem? Are we going to lose quality in terms of the service? Are we going to impact different groups of users disparately? So these are all the questions that we have to ask before actually recommending to implement this principle in practice. So for question number one, defining specific purpose for data collection in personalized systems. This is an observation that we make to suggest a specific definition. In personalization, data is collected not necessarily to deliver, but to improve the service, right? So if you think about personalized recommendations, you don't need user data to give people some recommendations. These recommendations can be either random or based on some aggregate popularity statistics. You do collect user data to tailor these recommendations to a particular user and to their taste. And so having made this observation, we can now try to tie a processing purpose to improvements in specific performance metrics. So we know what the purpose is. The second question is then, what does it mean to limit the data in relation to such a purpose? We can look at the specific values of the performance metrics and try to stop the algorithm from collecting data when we reach a certain point. And there can be different definitions of what that means. In what we did in one of our papers is we provided two potential definitions of limitation. The first interpretation, which we called global data minimization, suggested that we collect K items from each user such that the average performance of the system as measured across all the users that we have in the system remains within the threshold. Then we proposed another definition we called per user data minimization, which suggests that we should collect K items for each user profile, but such that the performance of the model for each of the users remains within the threshold. And so the third question, what does it lead to if we actually implement data minimization in the context of personalized systems? We investigated that in the context of recommendations. So just to give you perhaps an overview of what the structure of the experiment and this domain was. We had a recommender system that was trained on some background system data. And so this data can be historical, purchased, or say collected from another market that doesn't need to minimize the data. And so in our experiments, we assume that this is either a KNN, so neighborhood-based recommender, or SVT, so based on matrix factorization. And then we have a set of minimizing users. And for each of these minimizing users, we have an observational pool. So this is the data that we could potentially feed to the recommender system. And part of this data is going to be selected by a certain minimization strategy to be fed to a recommender. And some of this data is going to be minimized out. And then we have a test set on which we can measure what happens to the performance. And we've run these experiments using the MovieLens 20 million data set. So what were some of our first findings? What I'm plotting here are sorted RMSE error values for the population of minimizing users. And RMSE is one of the standard evaluation metrics that essentially compares the values of the recommendations over all of the test data. The system for which we're minimizing here is a KNN user recommender. Here, as a minimization strategy, we selected just n random items from the observational pool for each user. But we observed similar trends for other minimization strategies as well. Different colors here correspond to different minimization intensities. So how many items from each user profile we actually feed to the recommender system. The black line here shows the performance, so the distribution of the error values across the population of users when we don't minimize at all. So we feed all of the data to our recommender system. And these pink and brown lines show the performance of one item oracles. So they tell us the upper and lower bound of the error that we could potentially reach when selecting just one item from each user profile. And then different colors in between correspond to different intensities of minimization. And there are two high-level observations from this plot. So the first observation is that it looks like on the population level, the error distribution remains relatively stable as we minimize. And the second observation is that often we can minimize out large portions of data. For example, we can just leave 7 or 15 items without losing that much quality in terms of recommendation. So now, is this already enough to recommend that, we can just minimize data? It's okay. We're not going to lose much, but not yet, because recommendation systems, recommendation algorithms might differ in their robustness to minimization. So, for example, what happens when we replace a KNN recommender with an SVD recommender? It turns out that in our experiments, SVD seemed more robust to minimization. We could leave out even more data from user profiles while keeping the quality of recommendations intact. I also want to briefly talk about our insights on per user data minimization. So the experiment so far suggested to us that minimization is feasible globally. The quality of the system as average overall of the users remains relatively stable, even if we throw away a lot of data. But what happens per user? And so what I'm plotting here on the right is exactly the same data as the data that I'm plotting on the left with random minimization for KNN recommendations. But now the data points are sorted only by the error value of the full data predictions. So if, for example, I look at the data point here, all of the data here vertically corresponds to the same user. So we can see huge variability in the additional error that is incurred by minimization for different users, right? So what these two plots tell us together is that minimization seems feasible globally on a per model level, but it hides disparate impact to individual users. So our question at this point was, if there is a disparate impact to individual users, can we somehow predict who these users are going to be based on some characteristics of the user? And in a regression analysis, we examine whether there is any correlation between the error delta incurred by minimization and certain characteristics of individual user profiles. So we looked, for example, at the number of ratings in the user profile, average rating value, average popularity of items, the number of genres they have in their profile, movie genres, their average similarity to all system users, and their average similarity to their closest 30 users. And we found no strong correlation between these error deltas and any of these characteristics. What we found instead was that there were complex interplays between individual user characteristics, the population data, the base recommendation algorithm we used, and the minimization strategy. For instance, we found that for SVD recommendations, if we minimize data by selecting the items with the highest ratings, the incurred error will be higher for users who generally give lower ratings. While if we select the ratings with the lowest value, the error will be higher for users who generally give higher ratings. So all of these findings generally complicate the implementation of data minimization, because it's really hard to give recommendations or to predict in which scenarios minimization is going to be helpful versus in which scenarios it's actually going to hurt the ecosystem quite a bit. So all of these findings are findings from our CIIR 2020 paper. We have another working paper, and I can just give you a sneak peek of some of the results we're observing there. So in this ongoing work, what we're looking at is whether we can automatically minimize data using active learning techniques. And what we're finding there, for instance, is that when we apply active learning techniques to ongoing data collection, we're going to have disparate impact on users in terms of how much data is requested from each individual user. So what this plot shows us here is the number of features that are collected and the number of users for whom we collect this amount of data. So we have certain users for whom we collect, say, 600 product ratings, while we have a lot of users for whom we are collecting just a few. So the question is this desirable? Or do we in our information ecosystems want to collect the same amount of data from everyone? Or is it okay that some people pay for the quality of the service others receive? Should people be able to choose to be these high collection users if they get a guarantee that they're going to get a good quality service in return? So all of these questions are really open questions at this point. Another interesting observation that we made here that I want to share with you is that when we collect features using active learning, we always have to instantiate the algorithm with some initial data at the beginning. And it matters a lot how we select this data. So when you look at this first column here, so we look at the performance of recommendation algorithms when we collect only 25% of the data using an active learning scheme. When we compare how the performance looks like for these active learning algorithms, and these are the orange and green algorithms, and we compare what happens to the performance of these algorithms when they are initialized with a random subset of data. So this is this random row here. And we compare it to the scenario where data is initialized using a random subset of users instead of just random selection of user item ratings. Or if we randomly select per item. So we collect all of the observations for all of the users for a particular item. And we observe that when we don't initialize completely randomly, but instead just select either random users or random items, the error incurred in the data collection process by active learning algorithms increases. And this has consequences because random user selection corresponds to a scenario where at the beginning your system has just a smaller population of users. So essentially you have new users joining to the system later on. And random item subset selection might correspond to a real situation where you are allowed or not allowed by law to collect certain information. So maybe you might not be allowed to collect people's gender. So lots of these practical questions as to what do people want in terms of how their data is collected. Are they okay paying for the quality of the service for others, and so on and so forth. So at this point, I want to summarize this part. Based on our studies so far, we know that global performance-based minimization looks feasible for personalization systems. Per user performance-based minimization is not straightforward. So different users might be disparately impacted by minimization. And algorithms differ in their robustness to minimization. There are lots of questions that we still need to figure out. So are there different definitions that we should follow? We've experimented with just a few, but definitely they are not the final answer as to how we should minimize in the context of personalization systems. Are these definitions viable, both computationally and legally? How to automatically minimize data for personalization, and which users or communities will pay most if we actually implement these the principle of data minimization in practice, and how do we prevent this from happening to communities that are already underserved by those systems. I want to switch the gears a little bit now and tell you how we operationalize different principles. So except for purpose limitation and data minimization, there are other principles such as fairness or transparency. And here, the key observation that we made is that systems need to be fair in relation to the result presentation. So how are search subjects presented to consumers? In our CIIR 2018 paper, we proposed a definition of fairness, and that was a definition of individual fairness. So how defining when a search system is fair to an individual user. So what this definition suggested is that a system is fair when, for each subject in the system, the attention they receive from the searchers is proportional to their relevance. So this is a definition we started with in the CIIR 2018 paper. If you're interested in some follow-ups, we had 2 follow-ups in 2020 and 21. So this paper here looks at how we can directly optimize for this definition in practice and learning to rank algorithms. And I know, I think Fernando talked about this work in one of the earlier talks in the series. And in our newest paper at the web conference, we looked at how we can actually measure whether this principle is satisfied in the output of search systems if we don't have access to all of the annotations with respect to the membership of individuals in different groups. I want to tell you a bit more as to what are the challenges of achieving equity according to this definition. And there is one big problem with this definition, and that problem is position bias, right? So position bias is this phenomenon where searchers pay disproportionately more attention to items that are ranked at the top of a ranking as compared to the bottom of the ranking, often irrespective of the actual relevance of these different items. And so this observation suggests that we actually cannot achieve equity of attention in a single ranking, because the factors that influence the attention items received from the searchers and factors that influence relevance are often very different. And before I tell you a little bit as to how we can fix this, I want to convince you that this problem is real. So what we look at here is the distribution of relevance in data sets from Airbnb. And we defined relevance here using the user rating scores for different apartment listings in Airbnb for different cities. And we normalized the relevance to form the distributions. So we want to see, like, what is the fraction of relevance items ranked at different ranking positions receive from the total relevance. And what we observed essentially that there are thousands of listings that are similarly relevant to each other. So essentially that these plots are so flat here mean that all of these items are equally relevant. So all of them deserve to be shown to the searchers, but of course, physically we cannot fit them in with the first page of the results. So how can we fix this? How can we actually achieve some equity if we cannot do this in a single ranking? So what we can do instead is to reshuffle rankings to amortize attention. And that leads us to a modified definition of equity of attention. Instead of looking at a single ranking, let's look at M rankings and require that amortized or summed over M rankings. Each user in a system receives amortized attention or summed attention that is proportional to their summed relevance. And of course, if we only cared about fairness, we would be perhaps done at this point. But both GDPR and the utility of the service depends on the quality of the results that we're serving to the users. So of course, if we reshuffle the rankings to achieve equity of attention, we're going to incur certain quality loss. And trying to balance these two principles, fairness and on the one hand and accuracy on the other, leads us to an optimization problem. And the rough form of this optimization problem is as follows. So we want to minimize unfairness over a set of reshuffled rankings, such that when we compare the utility loss for each of these rankings in a series, when we compare the reshuffled one to the original one, the utility loss is going to be bounded by a parameter that we choose. Without going into much detail, I'm just going to tell you that when it comes to specific measures for unfairness and utility, we use the L1 loss here. This has this property that when we reach the optimum of this measure, we are going to achieve amortized equity of attention. And we measure utility loss using NDCG, right? So one of the standard information retrieval metrics. The only difference to real evaluations is that here we're computing NDCG, comparing DCG of the reshuffled ranking to the DCG of the original ranking. So essentially quantifying how different is the ranking going to be in terms of quality when we reshuffle from the original. And it turns out that if we plug in these two measures, we can solve this optimization as an integer linear program. So just to briefly walk you through this formulation, we have binary variables xij. These variables are going to be set to 1 if we place user 1 in position j. If we do place user I in a position j, we have to update this user's cumulated attention by the attention weight of position j, so where they're placed. And we have to update this user's amortized relevance using, by adding the relevance user I has in the current ranking, which is parameterized by L. And of course, the solution is subject to the quality laws that they've mentioned, and without going into details, this essentially computes the NTCG using these assignment variables. And on top of that, we have some variables that take care of, that we create an actual solution to this problem. So essentially bijective mappings from users onto ranking positions. And just to give you a feel for what this mechanism does in practice, just an example result from a synthetic data. What we have here is a synthetic data set with 100 users where everyone is equally relevant, sort of coming back to that motivation I presented at the beginning of this part. The black line here corresponds to the situation where we don't amortize at all, we don't reshuffle rankings, and unfairness here grows linearly, and the slope of this line is determined by the difference between the distributions of attention and relevance. And different colors in this plot correspond to different thresholds for how much utility loss we allow. And what happens here is that all of these lines are, of course, hidden behind this line, because if everyone is equally relevant, no matter how we reshuffle the ranking, we're not going to incur any loss. And what this mechanism does is that when we have 100 users in a system under a situation like this, when we have uniform relevance, and we look at what we call the singular attention model, where all of the attention is focused on the first ranking result, we're going to amortize unfairness as measured according to this L1 loss back to 0 every 100 times, right? So what happens is that every 100 iterations, each user is placed in the first position exactly once. And this is a synthetic scenario, just to give you a feel for what this mechanism does. Of course, in practice, it's never as clean, right? We rarely have a situation where everyone is really equally relevant. And we also, unless the system enforces that, we actually have multiple ranking positions. So not only top one element gets all of the attention. And so what happens in practice is that very often we, depending on how much quality loss we allow, we do observe some of this amortization properties, but then essentially we do have to accept that unfairness is still going to grow over time. Model interventions, it turns out, are not enough to actually ensure fairness in the system. And this is something we discovered in some of our follow-up work. So if we want fairness to be achieved in practice, we not only have to modify the algorithms, but we actually have to look at how people use them, because here we use attention as a proxy for what people get, but attention doesn't necessarily mean that, you know, when I'm a recruiter on a job platform looking at the ranking of candidates, I'm going to select people that are actually ranked at the top. So every researcher has their own societal and cognitive biases that are going to influence who is selected in practice. So just to briefly tell you about the experiments that we run to understand how specific interfaces and design choices influence how people make these selections in the societally critical applications. We looked at a platform it's called Donors Choose. And this is a platform where schools in the United States can crowdsource funding for their educational projects. So these can be buying new tools for the classroom or funding a field trip, things like this. We run active experiments on a proxy to this platform to try to understand how specific design choices and interfaces are going to influence which types of schools donors pick to donate to. We looked at a number of different interventions. So one example interventions that is highlighted here was that in the original Donors Choose website, we have a search box that allows people to search projects or search schools by their zip code or city name. But what we've observed in the behavior of the donors is that they have a tendency to donate to schools that are local to them. So for example, from the same city or from the same state. And we ask ourselves, what's going to happen if we remove this search box? What's going to happen to the distribution of donations? And essentially what happened is that when we presented donors with a web page that didn't have this location search enabled, they started donating to schools that are farther away from them. And this can have consequences because very often there's a geographic disparity in how much people earn. So if richer donors tend to donate to schools that are in their local neighborhood, the website perhaps does not satisfy their societal goal of actually distributing funding to schools in need. Another example that we've observed of a very simple intervention having an impact on the distribution of donations was showing the donors the level of poverty a given school has on the ranked list of the results. So this is the original design of this webpage, and this is the design with our intervention. So nothing changes, but we just show what is the level of poverty of students in the school. And it turns out that this actually has quite a tangible effect, again, on the distribution of the donations that we end up with on the platform. So what I'm showing here is that we can focus on this highest level of poverty. So these are the schools where the biggest number of students come from families of high poverty. And what happens is when we switch from the design that doesn't show this information explicitly to the donors, this is this green bar here, and compare that to experimental condition where we do show this information explicitly, that we can see that this has a huge effect on where people are directing their donations. Interestingly, this this intervention does not have as much effect as actually changing the ranking to be poverty-based. So if you rank the schools by the poverty, this has the biggest effect because of the position bias and perhaps because of other biases that people have, and simply utility constraints, because no one has the time to go very far down the ranking. And without going into much detail, I just want to mention another line of work that we have that is related to transparency and the right to be forgotten in search systems. So coming back to this abstract depiction of what an information access system is, when we think about users who are displayed in the ranking results, these users are exposed to the searchers in the context of specific queries. So these queries might be sensitive, related to, say, diseases or financial problems, or they might be unique identifiers, for example, email addresses or phone numbers. The question is whether we should provide search subjects with information about which queries expose them in the top K ranking results, either because of privacy awareness, either because of transparency requirements, that is, making sure that people understand how search systems operate, or perhaps because of the right to be forgotten. Perhaps users should be able to request the search engine that they are not displayed in the top K ranking results in response to particular queries. And with this, I want to end the presentation. I hope this talk provided you with an overview of the space of information retrieval and information access systems interfacing with the tech law. And I hope you have a better understanding of the types of questions that one has to ask to operationalize data protection laws and data protection principles in practice, and the types of insights that we can offer back so that these laws are made better and made more useful, more effective. Thank you.
Thank you, Asha. Thanks. It was a really nice summary of your work in this domain, and I personally enjoyed listening to your talk. So it's the Q&A time. We have plenty of time, about 10 minutes. There are a couple of questions in the chat, both from Bruce. So the first question is, doesn't data minimization mean that a search system will always work poorly on tail queries? They will never gather enough data to improve queries that occur infrequently. Also, the distribution of queries changes rapidly over time, so we have to keep gathering data to stay current.
Yes, this is a good observation, and there are a few factors that impact the answer here. So starting with the final part of your question, keeping the data up to date, there is another requirement in GDPR that actually requires service providers to keep the data accurate and exactly up to date. This is not as much of a worry. Essentially, the way we imagine this in the context of data minimization is that what you would do is you would collect new data but discard the old data as soon as you realize that the data is not necessary anymore. And in our experiments, we did test minimization strategies that follow this this idea. So instead of selecting random items, we just selected n items that are sort of most fresh, and we had similar observations. So random minimization and the most recent n items minimization performs similarly. So it's okay to collect new data as long as we discard the old data that is not necessary anymore. So I guess keeping the system up to date is not a problem. It's actually, in a sense, a requirement. Now, in relation to the tail queries, this is a concern. The way I would think about this scenario is that data minimization requires you to, again, requires you to minimize in relation to a purpose. So if you say, my purpose is to serve the users well, including on infrequent queries, then it's okay to collect and keep data for this purpose. So it doesn't say you should just collect K items irrespective of what happens. If you want to have 100% quality or as much of a quality as possible on infrequent queries, then it's okay to collect data for this purpose.
I made that because
Sure.
when you show that graph of the decrease in payoff, that always happens in search systems because you have once you've learned popular queries and do well on the popular queries, then because the infrequent queries are infrequent, improving 1,000 or 2,000 infrequent queries doesn't improve the performance over millions of queries, but it makes a huge difference to individual users. So those sort of aggregate graphs hide very important performance issues for search engines.
This is true. And similar concerns are related to users who are perhaps more, let's say, average in their taste and their behavior, and users who are more unique in their behavior. I think perhaps this is parallels the example that you've just given. So it's a concern that when we minimize data, we would be able to collect very few data from users who are well represented on average by the behavior of other users. And we have to collect a lot from users who are perhaps more unique in how they behave and what their taste is. So it's definitely a concern. And perhaps a way to approach this would be just to give users an option to choose where in this trade-off they personally want to be. Perhaps the users who are less, who are more unique are also the users who issue those infrequent queries. So if those users choose that they want to be high collection users, if they're guaranteed a better quality of a search result, the search results in return, then
I can just imagine people saying, I'm just an average person. I have no special consideration.
That's right. And interestingly, I think since 2019, I might be misremembering, I think Google changed their data collection setting for new users who join the system. And by default, I think their search queries are deleted after 30 or 60 days. I might misremember the exact number, but and so that corresponds again to that situation where you keep the data fresh, but you remove everything.
Well, you could throw away an awful lot of data about the popular queries and still have plenty, as long as you kept gathering data on the unpopular queries.
Yeah.
Bruce, do you want to ask your second question?
Yeah, I was just, when you were talking in the second part of your talk, you were talking about rank attention versus the relevance and fairness in that respect. There's so many definitions of fairness, but for search, it isn't topic. I never see people discussing all the work on search diversification and topic diversity enough with respect to discussions of fairness, because to me, topic diversity is potentially a better approach to some aspects of fairness than simpler rank attention models. Well, I just wanted to get your reaction to that. Why people don't discuss topic diversity and diversification in presentations on fairness.
I think maybe this is just a terminology mismatch. There are some works specifically focusing on group fairness, which apply approaches that are similar to.
Let's thank our speakers, even though she's not here. And I think if you have questions, I see that Jeremy there are actually a couple of questions in the chat. So please feel free to send an email to Aja. I'm sure that she'll respond to your questions. Okay, and thanks everyone.